videos 22 and 23, so check the description for links to those videos if you haven't seen them. This video is about being able to get a visual intuition for what the Ricci tensor means. I'm going to cover the more algebraic mathematical properties of the Ricci tensor in a later video, Tensor Calculus number 26, so you can watch that video as well if you want to learn more. So both the Ricci tensor and Ricci scalar can be thought of as summarizing the Riemann tensor that we learned about before. The Ricci tensor tracks volume changes along geodesics. So as we can see in this picture, if we take this rabbit and make all its points travel along geodesic curves, it actually shrinks in size. So the Ricci tensor tells us about how volumes grow or shrink as they move along geodesics. And there are two geometrical approaches to understanding the Ricci tensor that I'll discuss: sectional curvature and the volume element derivative. Also, the Ricci scalar is a number that's used to compare the volume of a ball in curved space to the volume of a ball of the same radius in flat space. So, as I said, the Ricci tensor is the thing that helps us keep track of volume changes along geodesics. So let's take a look at an example of this on a 2D surface, the 2D surface of the moon. Let's say that we have two people standing on the moon's equator facing north, and both of them are going to walk straight forward along geodesics that point north. Because of the curvature of the moon's surface, these two people will naturally get closer and closer together until they meet each other at the North Pole. And if we imagine a circle sitting between them, this circle will get smaller and smaller as they each move farther and farther along their geodesics. So in some sense, the change of the size of this circle given by the Ricci tensor represents how quickly these two people get drawn together. And this is why the Ricci tensor represents gravity in general relativity, as we can see here in the Einstein field equations. The more space-time is curved, the more quickly bodies will get drawn together. So in general relativity, gravitational attraction is just the natural result of curved space-time. It doesn't require any forces like we see with Newtonian gravity. Now, the Ricci scalar keeps track of how the size of a ball in curved space deviates from the standard size of a ball in flat space. Now, when we're thinking in two dimensions, a two-dimensional ball is basically a circle. So if we were thinking of a plane in two-dimensional flat space, a two-dimensional ball would basically be a circle in this flat space. So thinking in two-dimensional flat space, if we took this circle, the area of this circle would be given by the blue colored portion on the inside, and this is the standard flat circle. Now, if we were to live in curved space, say living on a giant sphere like the moon or a planet, we could also draw a circle with the exact same circumference. So this circle in flat space and this circle in curved space have the exact same perimeter. But if we were to look at this circle in curved space and ask what its area is, we'd get this entire blue region here, which is sort of like an upside-down bowl that sits on the sphere like a cap. And the area of this cap in curved space is actually larger than the area here in flat space. So even though these circles have the exact same perimeter in both cases, the circle in curved space can fit more area inside it because of the nature of curved space. And the Ricci scalar helps us quantify how much more space we can fit inside this circle compared to the flat space circle. So through the power of curved space and the Ricci scalar, we can fit a lot more space inside a tiny boundary. And this is a phenomenon we often see in science fiction and fantasy. If we think about the TARDIS from Doctor Who, or Mary Poppins' magic bag, or that tent from Harry Potter, all of these things are bigger on the inside. And that's because all these characters are experts in differential geometry, and they know the power of curved space and the Ricci scalar. Okay, so we've looked at some visualizations, now let's look at some real math. There will be quite a number of mathematical concepts in this video. We're going to start with geodesic deviation, then talk about sectional curvature, then Ricci curvature, and finally we'll get to the Ricci tensor. So we're going to cover a lot of topics, but it will ultimately lead to the Ricci tensor. Recall that I use any of these three notations for basis vectors, and they all mean the same thing. And I'm hoping you recall from previous videos the formula for the Riemann tensor and also its components, which are computed using the connection coefficients. Now, recall that when we have a family of geodesic curves with a tangent velocity vector field v, we can also look at the separation vectors along these curves, which are given by the vector field s. And we showed that, starting with the standard definition of a geodesic, which is parallel transporting a vector along itself so that the covariant derivative of v in the direction of v is 0, we can take the covariant derivative again in the direction s on both sides, and then subtract and add this term. And here is the definition of the Riemann tensor when the Lie bracket is 0, and here we can swap the order of v and s using the torsion-free property. So we found that the second derivative of this separation vector s, which is also called the geodesic deviation, is given by the output of this Riemann tensor expression with a negative sign in front.